Hi. Am I audible?
Yes, ma'am.
Okay, so have
Yes,
you
ma'am.
guys been able to do questions from graph theory?
Yes, ma'am.
Okay, we'll take up, if there are any doubts, we can take up at the end of the session. For now, we'll do some questions, some solve with us questions from graph theory. So this is the first question, and we'll try this out.
Ma'am, answer D.
I'm option D.
I tried it out. Let's see why other options are not possible. There are four vertices, A, B, C, D. Five actually, A, B, C, D, E. And we have to write down the degrees of these in this order only. And the possible degrees could be, now if A has 4 degrees, that means if you draw four vertices here, this is a pretty simple one. So you can just try to draw it. If A has four, that means it's connected to all the others, right? And then if B has four, that means it's also connected to all the others. That means this. And then the others can't. Now, if this has, C has two, you can already see that C has three, right?
Yes, ma'am.
A, we drew four, and then for B, we drew one, two, three, and four. Okay, this is extra, right? CD, we have not decided yet. So this was for four, four, and then if you draw for two, so if C has two, it has two, okay, and then D cannot have one, right? It already has two edges. That means this is not possible. So the first option is not possible. Now, if A has, we remove all these things. If A has degrees, that means it's any two vertices. And let's say it has one vertex, because you can do it this way, but it says that your E has two edges, right? So let's just do it with E to make more sense of this option. Then A has two, E has two, uh, rest everyone has one, right? So if this B's one is already done with A, then and C and D are left. That means they can have one with each other. That's the only possibility left. And then E cannot have the other edge with anyone else because this is completed, right? This option can't be correct. These two are wrong.
Ma'am, why E can't
And
have?
because you already have A2, so A already have two edges, B already has one edge, C and D already have one edges each, then E cannot have any edge with anyone else, right? Because their edges are completed, and
Okay,
E
ma'am.
still has. Okay. And coming to this one, C is like obviously true. No, none of the edges can have, none of the vertices can have five edges. Because if you have five vertices, you can have at most four edges for each vertex, right? So C is obviously incorrect. And coming to the fourth one, let's see how this one's possible. If you have this A, B, C, D, and E, then A has four. That means it's connected to all the four. Then B has three. So one is this, and C and D each have two. So that means let's have these two. So in this case, C and D each have two. B has three, and E has one. So this makes sense, right? So this could be the graph for this one. So this is the correct option.
Ma'am, for the
Yes.
second option, if we
Yeah.
connect A with D,
Okay.
sorry, A with E, D with A,
1 second. You have A, B, C, D. And you're connecting A with D. Okay. Then what was your doubt? Does anyone have any doubt in this question, or can we move on to the next one?
Yes, ma'am.
Okay. Then we'll move to the next question. And this is the next question. Give this one a try. It shouldn't take more than 1 minute. So have a minute and try this out.
Oh, sorry, ma'am, I got disconnected.
Yeah. Yeah. What's your doubt?
So I was saying that if we connect A with E
Okay.
and A with D
Okay.
and B, C, E
You're connecting B with C.
and E, yeah, C with E.
Okay. Then C is supposed to have only one edge, right? And you have two here.
Okay, got it.
Ma'am, in the fourth option D,
Yeah.
B is supposed to have three edges, right? In the figure you draw, I think I am not able to identify the third edge.
Which option are you talking about?
Fourth option, the right one.
Yeah. So this A has four edges, 1, 2, 3, and this is the fourth one. Then B is supposed to have three, so 1, 2, and 3. C and D each are
Oh,
supposed to have two, so there are two from each. And then
okay,
E
got it.
has only one, so it's
Okay,
this.
got it. Okay, I thought D is B. Sorry. Thank you.
Okay, this is D, this is E, and this is B. Okay,
Okay, thank you.
give this one a try.
Option D.
Ma'am, D.
Okay, so in this one you have to find the number of so it says maximum number of non-zero entries in an adjacency matrix of a simple graph having five vertices. So if you have five vertices, then the non-zero entries give you the edges, right? So for each non-zero entry represents an edge. So the number of edges is equal to the number of non-zero entries. So you simply have to find the number of edges. That is the maximum number of edges possible. And we had a formula for that, which was n minus 1. And why aren't we doing n minus 1 by 2? Because it's a simple graph taken. So simple graph is which has no self loops and other anyway we don't even have that in option. So n minus 1 if you do, you'll have 5 into 4. And for that
What
means
did you
you've
say,
taken the
ma'am? What did you say? Which does not have a cyclic? Uh, you said something like it's a non-zero matrices in an adjacent matrices. There is.
I'll come to that. For this one, let's just first try out this formula. And the other one we have n minus 1 by 2. That is for so this one is directed graph has more number of edges, right? So this one is for directed one and this is for undirected one. So this and this so this gives you 5 into 4, which gives you 20, and this gives you 10. 10 is anyway not in the option, and so it should be 20 only.
What is the definition of simple graph?
It's basically a graph with no self loops, and I guess no edges. So two vertices should not have more than one edge. That means no edges in both directions. So this
So
time.
does it mean it should be a DAG?
Ma'am,
No,
can
no,
you
it's
give an
not a DAG.
example of that non-adjacent loop?
Non-adjacent. No, we're not talking about adjacent and all. We're just talking about this self loop. Self loops in the sense we're not doing this thing here, right? When you have a vertex, you don't take this thing. So you don't take, this is called self loop. That means V1 to V1 we don't consider, right? This thing we in matrices itself, we consider V1 to V1 entry to be 0.
So, ma'am, here n-1 representing the number of edges.
So n is the number of edges. N is the number of edges, and n minus, this is the number of maximum
Maximum.
number of edges a directed graph can have.
Ma'am, n is vertices, right?
Yeah, n is the number. Did I not say vertices? It's n is the number of vertices. Okay. We have a formula for maximum number of edges, right? We did this in summary class, which is this. And then this is anyway not an option here, so you don't have to worry about it. Is that okay?
Ma'am, we got to know that it's a directional graph from the adjacency matrix.
No. We didn't get to know that it's a directed graph from the adjacency matrix. Either it's directed one, even if you look at the undirected one, the number of edges should be this 10. But you don't have 10 in options anyway. You only have 20. That's why we're taking 20 only. Is that okay?
Yes, ma'am.
This
Ma'am,
is direct
what's the
formula based thing.
of edges?
What?
Formula for number of edges.
Okay, for number of edges, this is for a directed graph. It's nn minus 1. And for an undirected graph, it's this. Nn minus 1 by 2. Is that okay?
Yes, ma'am.
Okay. Then coming to the next question. This is the next question. Give this one a try.
Ma'am, 3.
Okay, 3. How do you get 3? If we just look at this in a cycle, if you look at this thing, just this, you have B, then A, D. In fact, you don't even have to look at this one. If you look at just these these 4 vertices, you have this thing, right? That means each vertex out of these 4 vertices is connected to every other vertex, right? Just have a look at this thing. That means if you will color this something, you can't color these 3 with that color. If you pick red color here, you can't color these ones red. If you choose blue here, then you can't choose blue in these 2. That means for all of these 4, you have to have 4 colors, right?
Ma'am, 5.
Okay, so it's definitely not 3, right? 3 is not possible because these 4, the inner graph does this graph only. Even if it was just this graph, it doesn't allow you to have 3 colors. You should at least have 4 colors. And there's this theorem in graph theory, which is obviously not done in your syllabus, but for you to know, for every graph, planar graph, but this is not a planar graph, right? That theorem is for planar graphs, actually. I don't think it's applicable here. For every planar graph, you can, 4 is the maximum number of colors required to solve the graph coloring problem for any planar graph. But this I don't think is a planar graph. It crosses, there are edges that are crossing each other. So I don't think this is a planar graph. Let's leave
Ma'am,
it
just a
this
doubt
one.
between like is what's a planar graph? Just a little confusion.
A planar graph is the graph in which you keep every edge in the plane. In the sense, in simple words, it's this thing. If you have vertices, then the vertices shouldn't be crossing each other. Now, what happens is if you have this thing, now this is not a this is planar only. Why is it planar? You need edges to not cross each other. Now you'll say these two are crossing each other, but they can be made in this way. Now, if you'll make them like this, now no edges crossing any other edge, right? So this is a planar graph. But there are graphs now. If you'll try to join this A, or if you'll try to join B with C, then you can't, right? If I want to draw one more edge, which is BC, then I can't draw that edge without crossing the already present edges in the graph.
So ma'am, you're
That will be a
saying
non-planar graph.
in
Yeah.
non-planar graph, the edges don't cross each other in a way.
In planar graph, they don't. This
Example,
is a non-planar graph.
the graphical map.
What?
Example could be the geographical map.
Yeah, the map of India. That's a planar graph. But if you have to look at a simple graph, this is also a planar graph. Because
Ma'am,
you can, though it looks
in
like the edges are crossing here, but they're not crossing. They can be made in a way such that no edge crosses any other edge. Yeah.
but it is looking in a way that CD and AE are crossing each other, the edges.
That's
But
why I explained here. You can make it in this manner: A, B, C, D. If you will deliberately try to cross that, then this can also be made into a non-planar graph. You can do this thing A, B, and then you can just say that I'm doing this, and then for C, I'm taking it to be this. So if you deliberately try to cross edges, that's different, but this can be made without crossing edges, right? The CD you have to join. A, B, C. Okay. If I take D here, C, E here, then this can be made in this manner, right? CD and, okay, you have A, E here. I thought it's CD and then it will
Do
be
the
a
middle, ma'am.
non-planar
AE
graph.
in the middle.
In the middle.
We can
Yeah,
go
you can
AE
make
across
this
in the
here.
middle.
Thank you. This you can take here, right? So in this one, it's a it's a planar graph because the edges don't have to cross each other. There's a way in which the edges don't cross each other. That's why this is a planar graph. And then this is a non-planar graph. There's no way you can. Is there a way this? Then this can also be made into this manner, right?
Yes, ma'am. BC you go in the middle and then
But
the
then
other
they're
two can
still
cross
crossing
AD.
each other.
No, BC you take
You
to the
you
middle
don't
and
need
AD.
this one.
Yeah.
So for non-planar, you will need DA is already there, DC, DB. A is already connected to all, and C is also
Another
already
point.
connected to all. So
DC can be moved from another, like across A.
this can't be actually non-planar because we've made all possible edges. This has to be planar. For this, you'll need at least 5 vertices, I guess. Then, if you'll take 5 vertices, then I think it's going to cause a problem for you to have a planar graph. And you will join these two in similar manner. This, and E needs to be joined to every other vertex, right? Now, for E to join to D, this will have to cross this edge, I guess. There's no other way possible for this to be a possible edge in this graph. There has to be edges crossing each other. This will be non-planar. That means any graph that has 4 edges, we've just proved it here. Any graph with 4 edges, 4 vertices is planar only. because we've made all possible edges here. There has to be a possible number
So
of
ma'am,
edges is 4 into 3 by 2, right? So it's 6 edges, 1, 2, 3, 4. Or one edge is left. No, it's done, right? 1, 2, 3, 4, 5, 6. So all 6 edges we've made here. That means it's a planar graph. Yeah.
So, ma'am, the point you said that in a planar graph, it is always 4. What was your point there?
My point was that if there's a planar graph and then there's a graph coloring problem in that graph. So any graph which is planar and you've been asked the minimum number of colors that you need to fill that graph, the graph coloring problem is there, then there cannot be more than 4 colors. The
No
maximum
matter
number
how
of
ma'am, in
many
colors
general,
here
we
would be
can
4.
say that our non-planar graph have the edges, I mean intersect, in which
Yeah,
there is an intersection of
they're
the edges, then we can say
intersecting
that is
each other.
non-planar. Okay.
Yeah, it's non-planar, but make sure that there is no way possible for you to make it in a non-intersecting way. Like this one can be made like this without intersecting any edges, right?
Yeah, ma'am. Yes.
So this is still planar.
Yes, ma'am.
So, ma'am, you said that in a planar graph, no matter how many vertices are there, the minimum number of colors should always be 4.
Yeah, not minimum, not minimum, maximum. There
Maximum.
cannot be more than 4 colors. Minimum
Okay.
there could be 1.
Okay.
Okay. Now coming to this one, you at least need 4. So that means the number of colors required. Let me just represent that number of colors required is greater than 4, right? Now let's check if 4 is possible here. Let's do it here only. If I use red here, and then I can't use red here, here, and here. So let's use it at A. Then we can use it at I or H. So let me just use it for I. And then starting from here, your J, B, and C, G can have same colors, right? Because they're not related to each other. So J, B, and G can have same colors. Your E can have that same color too. And C can have that same color too, right? There's no problem.
Ma'am,
No,
there is a connection
no,
between C.
yeah, this cannot have. There's a connection here. Let's not take this one. And then one more color we're left with. Let's take that white only. So this is white, and this is white. So we're done. Wait.
Ma'am, then what is the maximum colors for non-planar graph or minimum?
Different color, ma'am.
From B also blue is there. You cannot color it, right?
Yeah. This one's also. That's why there are no 3 colors. Thanks. So you can't color this one too. So if you're coloring these 3, then yeah, then you can't color any other. This you can't color. This with this you can color blue, right? Because this is
No,
not
ma'am.
connected. No, this is also okay. This is also connected to B. This is also connected to B. These two connected to B. This connected to this. Okay, so that's it. Blue you can't use anywhere else. Then in this one, if you use green here, you can use green here, and
We have to use another color.
another color, and then one more color you'll need. Let's try to see if it can be done in 4 colors. I think it's possible in 4 colors. Let's try that. So
Yes, ma'am. Previously, it
we need different. Let's start with this one only because they're all connected to all the others. So let's start from here. Different color for this, different for this, different for this, and different for this one. And then this cannot have red, so you can do this as red. And then this also you can do red. You can't do this one red, and this one can not be red. These two can't be red. So you can use green in this one. Then
H can also go in green.
F can be
H
blue.
can,
H can
let's
be
C we have taken white, right? So C can be white,
Yeah, C is
H
white.
can be white, and J can be white.
J can be
They're
white.
fine.
F can be blue.
And F can be blue. So we're done with 4 colors, I guess. We don't need a 5th color for this. Start with the edge, the vertices that are connected to almost all, and try to because this one we started with, because these 4 are connected to all the other 3 in this particular graph. In this one connected to all the other 3. That's why we have to take at least 4 colors. So let's start from this inner one only, and then you can find the remaining ones. Is that okay?
Yes, ma'am.
It's always a planar graph.
I have a question.
Yeah.
So if like the top one, E was not there and it was just a square, like the outer square. So to make it planar, can we take the inner part outside?
This one is not E. Which vertex are you talking about?
Sorry, F.
Okay.
F. See it.
Yeah. So
So
what's your point?
if it was not there and it was just a square, outer square.
If this wasn't here, then these
Yeah.
edges won't be here. Then what?
And so can we like take the inner part outside to make it non-planar?
Yeah, you can do this thing. If these edges weren't here, if you're ignoring all of these things, then you can try this thing. To join A and D, you can do this thing. Then
And C and E can go
C,
connect.
D, and A, E are also causing problems, right? So C, D, you can do it in this. C and D, you can do like this. And yeah, I mean, and then what's left? A and E is also left, right?
Ma'am, if we connect C and D, then it is crosses the A and J.
C and D? Yeah, it also crosses here. Thanks. This one will also cross. If you will try to make AE edge, that's also going to cross.
No, ma'am, what I'm saying is like if we take this inner part outside and we take the square inside of this, like expand it.
Sorry. Yeah.
So now G will be inner in the inside and it will be connected with the D.
Okay, you want to take G here.
Yeah. So can we do that?
And you're taking all the outer ones on the inner part.
Yes.
Here
So
you will
that
have I. Here you will have H. You can connect these. And then, so what edges are we left with? AD is there. These are obviously there.
D
These
we
ones
can
have been
take
taken
at the
inside.
bottom.
we have left F.
Yeah, F we're removing this entire thing. The question is, if we remove this entire thing, F and every edge that is with F, if we remove that thing, can this graph be made into a planar graph? Or is this a planar graph in simple words? What's left? Is it a planar graph? That's the question.
Yeah, it should work.
And then B, you have to join with C. Yeah, it's working, I guess. E and yeah, that's it, right?
From
Any
outside, you
edge
can
that's
connect
left?
A and
AE
D.
and
A
BC.
and D are getting connected and D and C.
A and D we've already joined, right?
A and E.
A and E and
D and C.
D and C. We cannot connect them.
yeah,
Okay.
B and
So,
C will be a problem then. Yeah.
okay. So I just wanted to know that we can distort it like this, right? Like we
Yeah,
can.
yeah.
Okay.
You can try to make things like this, but no edges should be crossing each other.
Okay. Got it.
Ma'am,
Thank you.
when you just saw this graph, you said that it's a planar graph. So if we don't able to recognize it in the first instant like you did, we have to check it in like an alternate way to check it. Like for example, ABDE it looks like a non-planar because it's intersecting. So we have to make it an alternate graph and check it if it is planar, like that
For a
only.
planar graph, you only have one leverage, that it cannot have more than 4 colors. That's all. You don't know how many colors is it going to have. So
Yeah, ma'am.
because this is a non-planar graph, it can have more than 4 colors. You still have to identify the number of colors. So even if it's a planar, non-planar graph, you'll have to do this thing of trying to check which color works and which doesn't, how many colors you need.
Or we can make an alternate graph like the way you are doing it in order
So you
to.
don't need to make, that's just for you to recognize if it's a planar graph or not. That's it. And in this one, even if you don't recognize if it's a planar graph or not, that's this, in this one, it's helpful because it helps you. And the planar thing is not even helpful here because this is not a planar graph. So we've not made use of planar graph anywhere in this question.
Ma'am, the answer for this question is 4.
Yeah, it's 4.
I remember the same question in PYQ. The answer was given 3. So I was also confused. Why is it 3? Because this cannot be achieved with 3 colors.
It must be a different graph then, or the answer would be
It was
wrong
the
then.
same graph. That is why I'm asking you. Maybe the answer given was wrong.
Yeah, then the answer is incorrect.
Ma'am, just one thing. In this question, the least number of compartment into which the warehouse should be partitioned is same as the color of vertices in the graph, like a little bit the definition.
Yeah, the minimum number of colors you'd require, right? If you have to group them, if you have to partition them, then it's obviously the minimum number of colors required so that no two adjacent warehouses have the same color. It's what's the question? What is the least number of compartments into which the warehouse should be partitioned? So partitioning this warehouse, it's a graph coloring problem.
It's already given
Because
in
you
the
have
hint
to,
also.
yeah, it's given in the hint too. Even if the hint was not given, without the hint, it might be a little confusing because this is not given to you that the two compartments and the adjacent compartment should not be in the same warehouse or something like that.
Ma'am, I have a doubt.
Yeah.
If the maximum number of colors we can put in a non-planar graph is 4, then planar graph is 4, then is there something like this in non-planar graph also?
No, in non-planar graphs, we don't have this thing. The bound for maximum colors, it's 4 in planar graphs.
Ma'am, I have done in 3 colors. Can you check if I am correct or not?
Yeah, okay.
Ma'am, JBDH in 1 color.
J, B, D, and H.
FAI in 1 color. And C, ma'am, in my question, C and E is not connected. Okay.
Ma'am, just the thing was the property thing. Like if the hint was not given, it could have been a little confusing. So you
But
were
it's
saying
given,
that
right?
yeah, but the least number of compartment in a graph in generally is same as that no two vertices.
No, it's the question only says what is the least number of compartments into which the warehouse should be partitioned. So we don't know what is the criteria for partitioning the warehouses, right? the criteria is not mentioned. That is why you've been given a hint.
Okay, okay.
They don't say that the two warehouses should not have an edge. That's not mentioned in the question. That's why the hint helps. Without a hint, it will become a little confusing. Can we move to the next question? Give this one a try.
E and I. Option C.
Ma'am, E and I.
Okay, let's see. This is a BFS tree.
E and H.
Okay, let's check. E and H, someone just said. Let's check what are the correct options. So this is a BFS tree, and if you first is B and K. So if you join B and K, this now B and K can be a possible edge, right? Because even if K comes under this has been discovered under C, so it won't be mentioned under B. So even if there was an edge in the original graph, that won't be a problem here. So BK can be an edge. Then coming to M and N, M and N can be edges. So you start from here. The M and N can be edges for the same reason. Both the reason for both of these is same. For M and N and for B and K, the reason is same. Because you start with C, you get done with C. So anything that has come under C, even if it's under B and something else after it too, it doesn't matter. Because you don't write things again in a tree. Then coming to EI, EI is here. E and I. Now if I was under E, then you would be mentioning I here, right? Directly connected to E. First you get done with E and then you come to F. And the fact that I has been listed under F means that I does not have a direct edge with E. This cannot be an edge. That's one correct option. Then E and H. E and H cannot be an edge too, right? Because if E and H was an edge, then you'd see H under this. Because first you get done with E, then you come to F. That means this is also correct.
I didn't understand this. Can you just explain this again?
Which are you
E and
confused
H. E and
about
H.
a
E and I
particular?
is fine. Got the others. Only E and H, if you can explain.
This is H, right? First you start, now these are on the same level, and for the same level ones, you start with the one that's listed first. So E is listed first on level 1, right? Or level 2 actually. This is level 2. So you start with E. Now if H was under E, you write it here, right? Because first you start with E, then you get done with E, and then you start with F. So if you're mentioning something under F, that means that thing can't be under E. If that thing were under E, then you'd see that this entire thing under this. And this thing would not be here. Right?
Okay, got it.
So, ma'am, a vertices which is like left side vertices, it can be connected to right side its predecessors, but the right side vertices can't be connected with the left side predecessor. Means H is the H is the right
Ancestors
side.
you're talking about, I guess. If you're saying here,
Ma'am, like G can be connected to F, but H can't be connected to E.
yeah, G can be connected to F, right? Because it's all, yeah, G can be, this can be connected to all these, F, K, N. That works. H can't be connected to E, M can't be connected to M. And these ones on this side can't be connected to these ones.
Okay, the first discovery, the vertices which are discovered first can't be connected to the right side later discovery, means the bottom one. Okay.
Ma'am, a little confusion in E and I. Can you explain that?
E and I has the same reason. First you start with E, Now, if I is under E, so if I is under here, then would you not see I here directly? Because you first start with E, you start exploring E first, and then when you get exploring E, is when you start with F, not before that. So that means if your I was here, then why would you write your I here again under H? That has been discovered via E, right? It has been visited via E. Why are you writing this again here if E and I was actually an edge?
And I have a doubt. Can
Yeah.
E and F can be connected?
E and F can be connected, right? Because on the same level ones can be connected in a BFS tree. That's fine.
But how, ma'am? Like if E is connected to F, then the whole branch under below the F will be connected to E. Then D won't be discovered again, right? Then
What won't
it is an
you
undirected
first,
graph.
when you start with D, you first mention all the vertices that are directly connected to D. So if E and F are directly connected to D, then you write them down first, right? So your F would still be here. It won't come under E. Even if it has a direct edge with E, you would write F under D because first you write all the elements that are directly connected to D.
Okay,
Then
got it.
you start exploring the
Got it.
ones. Okay. Can we move on to the next question?
Basically, we can say that the end edge like G, L, J, they can be connected
Yeah,
because
G, L, G,
the
M, they can be connected.
to any vertices because it won't make a difference in a way.
On the same level, the vertices can be connected. So everything that's on the same level can be connected.
But at the lowest level, if there is an edge, can it be connected to the above?
That
Because
these are the lowest ones, then it
yeah,
depends. If you have this thing, then it depends what you're connecting it to. So I and just now we saw I
yeah,
can't be
ma'am, okay.
connected to E,
Ma'am,
and I can't be connected to G as well. You can't connect I to G for the same reasons.
Ma'am,
Yeah.
simply if it skip two steps, then it can't be an edge.
I was saying if you're skipping two steps, one step, two step, then it can't be an edge.
Yes, ma'am.
That's not how you do things. Then there are other possibilities where skipping two steps and you can still have that as an edge. Let's see this one. Okay, let's skipping two edges.
Ma'am, BK also it can't connect, right? It's a B is the first level, right? Level 1.
Yeah, BK you can connect because yeah, K has been already mentioned under C. So BK you can connect.
Oh, it is list visited. When C is
That's why
C is
there
ex-
could be an edge here. In the original graph, that's why you can have an edge because it has already been visited via C.
So
oh,
we can basically say to be an edge, it have to be on same level or an adjacent level, right?
You can just simply try making a tree and then see if it's possible if you can make a tree or not.
Oh,
Because
okay.
then I'll have to write down all the possibilities on the same level. On the same level, ones can have an edge in BFS that we've already discussed. And then the problem is with the skipping levels. So if you have this thing, so it depends where you're skipping levels. If you're doing this thing, then it's wrong. But if you're doing this thing, then it's fine. K and
Okay.
H can have an edge. E and H can't have an edge. And about skipping two steps. So if you have this thing, if you skip edge here, two steps is actually it works both ways. So if E and I can't be an edge because then it would come under this. And if you do it here, like where can I do this thing? We've done it on the this one. Let's do it this
F and
way.
I.
So if K and J you do, F and I, F F and I cannot have an edge obviously because else you would write I here on the same level as H. And then if you look at K and J, um, now if K and J had an edge, then this
Ma'am,
can also
HK
not
can't
be
have
an
an
edge
edge
because
because H will get visited before K. If
no,
it had an
HK
edge, it
can
would
have
be direct.
HK can have an edge, right? Because gets visited via F first, so H and K can have an edge.
But ma'am, the left side we will finish before we go to C, right? We'll finish D
Yeah,
before we
that's
go
why
to C. So if the edge was there, it should have been connected to K.
we're talking about this one, right?
Yes.
So if you start with E, then you get done with E first, then you start with F, you write H here, and then you start with
Yes.
this is we're done with. Then you start with K. Now if K and H were an edge, H has already been discovered via F, right? So you don't write it again.
Okay.
K and H can be an edge. K and J can have a problem because if K and J were actually an edge, then you will see J on this level. This is level 1, level 2, level 3. Then J would be on 4th level. But it's not on the 4th level, it's on the 5th level, right? K and J directly had an edge because you first get done with K and basically everything that's on level 3. First you get done with these vertices, exploring these vertices, and then you come to the vertices on the 4th level. So if J was actually connected to K via an edge in the actual graph, then J would be under K, directly under K. That is on the same level as H. Then you wouldn't be writing J under H again. So you can't have edges when you can't skip edges like this. So if you skip levels, 2 levels, 1 level and then 2 level, then that can't be an edge.
Ma'am, but what if like J is connected to H and K, and
That's
because
what I'm
H,
explaining. If it's connected to J, H, and K both, how you make a tree is first this is your level, right? Third level, E, F, K. Now first you start exploring this, then you get done with this. Then you start exploring F, you get done with F, and you're done with F on H only. You don't explore the next level. Exploration of F is done, and then you come to now if K and J actually had an edge, then you would explore K and you would discover M, L, and J, right? So J would be on this level, on 4th level. You won't see it on the 5th level.
okay, got it.
Easiest way is you start from here. You start with this vertex. Every vertex that has a direct edge with it has to be mentioned here before you come to this one. And then everyone that's directly connected to this has to be mentioned here before you come to this one. And once you've mentioned something, if you mention J here, you can't mention it again on any other level afterwards or anywhere else. Is that okay?
Yes, ma'am.
Ma'am, we can say that we cannot skip one level, like one
Yeah.
vertices. So can we take it as a
If
rule?
Yeah, you can take that as a rule. If
Like
you skip more than 1 level, then that's not an edge in a
okay,
tree.
okay. Like we cannot connect 3 level to the 5 level in a way. You are saying that.
No, you can't.
Okay,
3
ma'am.
level and 5 level cannot be connected.
But 3
Okay.
and 4 can be.
Yeah, 3 and 4 can be.
Okay, ma'am.
Ma'am, then
So
should
for
E
any, sorry, go ahead.
and then should be E and H should option E and H मतलब कि वो wrong होना चाहिए फिर तो.
I didn't say that. I said 3 and 4th can have an edge because K and H can have an edge, right? I
Okay.
didn't say that they would have an edge for sure. They
Ma'am,
can.
so
I don't understand why we are saying that कि E and H cannot have a edge and K and H can have a edge.
Okay. You
Or
start
the
with
difference
E.
is same. The difference in level is one.
No, it's not about the levels here. You start with E. This one is not about levels. Then you start, let's say you have a graph here. Then you go to E and see every vertex that has a direct edge with E, right? And that has not been mentioned yet. So if A has a direct edge with E, you won't be writing A here again. That's first thing, right? Because A has already been mentioned in the tree.
Ma'am, isn't it
So
about Q of the vertices?
you can say it's about Q, but you don't have to get into that thing. So first you get done with E. That means you write every vertex that is directly connected to E. That means that has a direct edge with E. You write that down here. And that has not been mentioned already in the tree. So it should not be A, D, C, D. You can't write A, D, C, D here, even if they have a direct edge with E. Is this
Can we
much clear to everyone?
Can I just ask one thing?
Yeah.
So if we read the question a little bit more carefully, and now it's making a lot of sense. What you're saying is that because it is said it is undirected, so E necessarily then gets explored first in an
Yeah.
undirected BFS, and therefore all of E's neighbors need to get explored before we move, and therefore E and
No,
H cannot be
not
there.
all.
Is that
They
right?
don't need to be explored. They just need to be visited.
They just need to be
Visited means,
visited.
yeah.
Okay. Yeah. Got it.
In
Okay. Thank
simple
you.
words, E needs to be explored first. Exploring E means writing every vertex that is directly connected to E, that has an edge with E. So you write down that vertices first, then you come to F. Then you write down every vertex that has a direct edge with F, and then you come to K, right? Now, if K and H had an edge, let's say K and H had an edge, then you already have mentioned H here. And once you've written something, you don't write it again in the tree, right? Is that okay? That's why K and H can still have an edge. Because if that was an edge, then you wouldn't be mentioning H here again. You'd simply ignore H and come to other edges with K, which is M and L, right? That's why K and H can be an edge.
Ma'am, you said that we cannot skip a two level in a way. It's a rule. Yeah, ma'am.
Yeah.
So it's same for the directional graph also?
It's same in directional graphs. If you'll have KJ and it's a directional graph, yeah, it's same for the directional graph too. You can't skip levels there too.
Okay, ma'am.
Okay.
In
Ma'am,
this
is it
ENH,
bottom layer to top layer, we cannot connect. We can able to, because it's Explorer, right? We can able to make a
the bottom one is this, the top one is this. Yeah, you can't connect
yeah.
this to this. Yeah.
We cannot.
Basically, you can't connect A with any level other than, and 2 also were not, 2 is it's already connected with, right? So can't connect it with 3, can't connect it with 4, can't connect it with 5th level.
ma'am? Ma'am, is N connected to L?
If you'll take N and L connected, yeah, they can be
Yes, ma'am.
connected, right? Because it's already, N and L can be connected. That's fine.
Okay.
If you want to take it as a rule, then you can take if there's a vertex on level N and N plus 1. This is N level and N plus 1 level. Then on the nth level, you can connect the vertex to the vertices that are left to it. This is left to it. Or by left, I mean this left, under K, under the left ones. You can connect it to all of these. That's fine. I think we've discussed this way more than what's needed. Can we move on to the next one?
Yes, ma'am.
Okay. This one's the last question. Give this one a try.
QRPSTU.
Ma'am,
UT.
UPQST. UPQST.
How can you start with Q? First, to start with Q, you'll need to get done with R first. In simple words, the question says you need an order to perform these tasks. These tasks are named P, Q, R, S, T, U. And for you to start with Q and R, you will need to get done with task P first. So if you start with Q,
UPQST.
Q does not need anything to be started with, right? So we can start with Q.
no, column 1 shows the task and column 2 shows the sets of tasks that can be performed only after performing this task. So only after performing this task can you come to these tasks. So for you to start with Q, you need to get done with R first. This is column first. This is column second. So you can do QR task only when you are done with P task. You can do Q only when you're done with R task. PR only when you're done with S. And same goes for others.
Ma'am, is it TUSPRQ?
You can start, the starting point is definitely T. Because T has, in this list, only T is missing. That means only T is independent of every other task. Here, only T is missing in second column. That means you can start only with T. Then
Ma'am, USPRQ.
you can go to U because U requires only T and U does not come in any other list. That means U does not require any other task. So U can be next. Then what?
SP.
S could be next. P is also fine.
RQ.
R needs S and R needs P. Both of them are done. R and Q needs R. Yeah, this one's fine. There could be other ways too. You can do T, then you can take S, R. R needs S only, right? No, it needs P too. And P needs S only. It needs U too. You can do it in this order too. TSU.
RPQ.
Yeah. Does R require P? No, right?
P
R
requires
requires P, right? R requires P.
PR.
Yeah, I think these are two possible orders.
Ma'am, can you explain it again? I'm finding it difficult to understand.
Okay, first is you only have to find one way you can do it. We're trying to explore more ways, but you only have to find one. And then it's better if you're able to find all. That's even better. So first this is first column, this entire thing, and this is your second column, right? This is first column, and this is second column, this entire column. So
why
and it says
first?
What?
Like TUSPRQ, and why we took T first?
Yeah, I'm explaining why we took T first. So the question first says that your column first represents the task and second represents the task that you can't do without this. So QR you cannot perform without completing P. So first you need to get done with P, then only you can start with the task Q and R. And first you need to get done with R, then only you can start with task Q. Same goes here. First you need to get done with T, then you can start with US. So only T is that element. T is that only thing that is not listed here. That means T. These are dependencies, right? But not dependencies. You can call them. They are dependent on these tasks, and only T is not present in in this list. This entire column. That means only T is that one task that you can start without requiring you to get done with any other task.
No prerequisite.
Yeah, you don't need any other task to be done to start with T. In simple words, T does not have any prerequisite. So you can start with T, and after T, you see U and S depends on it, and US and are not there in this entire list, right? So you can get done with U or S, whatever suits you. We've done both ways. So you can start with U, and then U requires P. So either you write SP, because S is not anywhere else. S is not here, not here. That means S requires only T. P requires only U. So you can either write this thing or you can do this too, because P also does not require anything. Okay, P requires S. P is here as well. So that leaves us with this option only. So you can't do PS because P requires S. P is here and it requires S. That's why you can't do this thing. And coming to this TUSP, and after P you can get done with Q and R, but Q requires R. That means you should first get done with R and then start with Q. So it should be this order. Or you can take it to be SU because S and U do not require anything else. U and S are only here, so they don't require any other task. The only prerequisite for U and S is T. That's all. Is that okay?
Okay, ma'am. Thank you.
Yes.
You can even swap SP after TU. That will also work. Yeah.
So SP, if you swap P, requires S. Yeah. So it won't work. Okay. So are there any other doubts from activities or anywhere?
Ma'am, I have a doubt in question number 4, ma'am. The EH part, the connection between EH. I am not clear with that.
Okay. If this is your tree, right? If let's say you have a graph and EH is an edge there.
Okay.
Now, if EH is an edge there, how do you make the tree for it? You come to this level first. Everything above it is fine, right? We're not changing that. Come to this level. And then you start exploring E. Exploring E means you start visiting every vertex that is directly connected to E. So you go to G. G is directly connected to E. Right? So this is your graph. If H is directly connected to E, EH is, if it's an edge, then you should write H here, right? Because first you get done with E, then you come to F. Right?
Yes.
So you should be writing H here. That means this cannot be a possible edge in your original graph, because if this were an edge in your original graph, then you would write H here. But your graph, this tree says that your H is here under F. Right?
Ma'am, but if we start discovering from F, then we can say that. No?
Why would you start with F if I've mentioned it 1,000 times that you have to start from this left side?
Okay.
So whatever you write first, you start with that only, and then you get done with that vertex first, and then you move on to the next one. Then you get done with this vertex, then you move on to the next one.
Yeah, ma'am. We have to start always from the left. Yeah, ma'am.
Yeah.
Ma'am, G to D cycle is possible, right?
G to D.
G to D, the same branch.
This one.
Uh,
If G to D, this is DFS, right? So G to D is not possible because firstly you're skipping 2 levels, 1 and 2. I've already said that skipping 2 levels, that edge is not possible. And second
so in
thing is,
that case,
if G was under D,
cycle is
you'll
not
have G
possible.
here.
Huh?
Yeah, this
So in
cycle
this,
is not possible. DG is not, it can't be an edge in the original graph.
but in graphs and all, they're showing us, right?
Which graph?
Some other question and all, they're making the cycle, right? From first level to second level. In graph, we can see, right? This kind of.
If this is the tree for the graph, then DG can't be an edge. Either that would be DFS approach or that would be a different graph. Tell me the question number, we can discuss it here. Are there any other questions from anywhere on the portal?
Ma'am,
except
can you
the graded
explain?
assignment?
Ma'am, can you explain perfect matching of a graph?
Ma'am, I have a doubt. in one question from practice assignment.
Which question?
Question number 5.
Okay, 1 second. Question number 7. This question, right?
No, ma'am. Question number 5.
Oh, you said 5. Sorry.
Yes, ma'am. This one.
So this is the question. And let V be the set of vertices and Vi be the maximum independent set, Vc be the minimum vertex cover. So you have to find the cardinality of Vi and Vc. So Vi is maximum independent set. Maximum independent set is basically there should be you have to collect vertices that are not directly connected to each other, meaning they should not have an edge, right? So if you start from this one, and then you can take this one, then you can take this one, and then you can take this one, right? So it's 4. And you can't have any other one. Even if you try it with any other choices, if you start from, so if you start with the outer ones, you're going to get the same 4. If you start with the inner one, then also it's going to be same. You can't have this one. You can have this one, can't have these two. You can have this one and this one. So it's obviously always going to be 4. The cardinality should be 4, right? You can't have more than 4. 4 you've discovered. That means the maximum independent set is at least it has at least 4 elements. Can't have more than 4 because you can't find any.
And
If you
ma'am, what
start
about
with the outer
V's?
ones, what?
That is clear, the Vi. And what about Vc, the minimum vertex cover?
Okay, then
What's
coming
that?
to the vertex cover, you need one vertex from every edge, right? So if you start from here, this is, if you take this one, this edge, and this edge is covered. These edges are covered. Then if you take this one, these 3 are covered. And what's left? These 2 are left. So you'll have to take this one. Just 1 second.
And we can take the diagonals one.
Take this one. So you'll get done with these 3. And if you'll take this one, you'll get done with these 3 edges. And then you're left with this. So you can take this one for this. And this one for this, and this. This. So everything's covered, right?
Just a little confusion in the definition, ma'am. It's the vertex cover are the vertex which are not directly like in a way.
Vertex cover is the set of vertices where from each edge you have at least one vertex. So you need one vertex from every, you have to collect vertices in such a way that if this is first, second, third, fourth, and fifth, sixth, seventh, eighth, then you have to collect vertices in such a way that every edge has at least one vertex here. So if this is an edge, you should have out of 6 and 2, you should have at least one of them here. Both of them can be here, but you need at least one from there. So you start with this one. If you start with this one, or if you start with this one, these three are already covered. So you take V2 we are taking. Then let's cover the outer ones first. So V3 take V3 to be next. So these three are also covered. These three, the outer ones are already covered. And then to cover the inner ones, you take this. Or you can take this too. If you take this, these three gets covered. If you take this, these three get covered. So this was V5 and this is V8. That order. Or the order actually doesn't matter here. Yeah. This would be it. Is it okay?
Ma'am, I have
This is vertex cover and it's actually the minimum vertex cover. Yeah.
can we say that total vertices are addition of independent vertices and vertex cover?
What?
Like the total number of vertices, that's 8 here, right? It will be summation of Vi and Vc.
Saying the
Not a
total number
summation
of
of
vertices is this. That's what you're saying?
Yes, that is equal to total number of vertices.
That's not, I don't think that's a rule. That's not always true.
Okay.
Ma'am, ma'am, perfect matching of a graph.
In perfect matching, firstly, you're familiar with matching, right? What matching is.
Yes, ma'am.
Okay, matching means it's a collection of edges. I'll just repeat it anyway. Matching means you collect the edges that do not have any point, any vertex in common. So if I take V1, V2 here, then there should be no edge in this collection which has V2 in it. So you should not be taking V2 or anything or V2. This should not be here. And same goes for V1. That's your matching. And perfect matching basically just means that in your graph, every vertex, so it's a matching. Your perfect matching is a matching, and then you put one more condition. That's first condition, and you put one more condition with it, which is each vertex should be covered in the matching. That's it. That makes it a perfect matching. That means if you have 4 vertices, then all the 4 vertices should be here. So V1, V2. So if your graph looks like this, V1, V2, V3, V4, then you can have V1, V2 and V4, V3. Now that's a perfect matching. You can have more than one perfect matching. You can have more than one minimum vertex cover, more than one independent set, a maximum independent set. These are not unique. None of them is unique. This is perfect matching is also not unique. And if you'll have 5 vertices or odd number of vertices, there's no way you can have a perfect matching, because no matter what pairs you try, at least one element would be left. One vertex would be left.
No, in this case,
So-
V1, V3 are matching, right? Just for my understanding. In the graph that you just drew,
This
they are
one?
not having adjacent edges, right? In this.
No,
Should
no,
it be
we-
V1, V2
so
or
your-
V1, V3?
Your perfect matching is this set. This set is called perfect matching.
No, I have a doubt in matching itself. Is V1, V2 we are saying matching, or V1, V3 are matching because there is no edge between
V1,
them?
V2 is a matching, no? Because they have an edge. In matching, you try to make pairs of vertices.
We have to make the
So
pair.
that no vertices are repeated. That's all.
Ma'am, we have to make a pair in a way they only have a direct edge.
Yeah,
That's what
only direct edges.
Okay.
In fact, it's a collection of edges only. That's
Okay,
why we say it's a subset of edges.
Thank you.
So, ma'am, when a question says that perfect matching of a graph is 2 or 3, what it trying to convey? Means what is trying to is 3 and 2 here?
What's the question? Perfect matching is 3.
Perfect matching of graph is equal to 3. So what is this means?
I mean, it's about the number of edges then, I guess. That's the only plausible interpretation of it.
Means the sets have 3 cardinality.
I still don't get your question. What exactly are you asking? What does the question exactly say?
Ma'am, it says the PM of graph is 3, where PMG is a perfect matching of a graph G, and there are four.
It says
PM of a graph is equal to 3.
It directly says this.
Yes, ma'am. And where PM graph is perfect matching of a graph G. So I'm not.
That means there are
understanding
possible 3 perfect matchings. That means you can have 3 perfect matchings.
Okay.
That's what it should mean. Yeah.
Ma'am, you said that if there is an odd number of vertices, we cannot have a perfect matching, no?
Because it don't cover all the edges, right? All the vertices.
Yeah. Yep.
And here the number of the vertex cannot be repeated in perfect matching, like in the pairs. Like V1 cannot come again in a way.
Yeah, that's also true for matching. You can't repeat vertices in edges. If V2 is here, it should not be there in any other edge in this.
That's
For
also
it
there
to be
in
a
the above
matching.
question, ma'am. In the question there was a definition for that. That is also, yeah, in the question. Just if you go up, that is also for the vertex cover, ma'am. Yeah.
Vertex cover. What's your question?
Ma'am, you said that there will, it's not a unique thing, na? Vertex cover.
Vertex cover is not unique. I meant that in the sense that you can have a different vertex cover. This is not a unique set. So a different vertex cover could be, you can take V1, V4, and then you can take V5, V8. That also works. That's also a minimum vertex cover. This is also minimum vertex cover. Is that okay? In that sense, I meant that this is not unique. Minimum vertex cover is not unique. You can have 2 different sets that are minimum vertex cover. Same goes for maximum independent set, and same goes for matching, perfect matching. Okay, anything else?
Question 8, please, in the same practice assignment.
Yeah, okay. 1 second. This one, right?
Yeah. The doubt is BD is a forward edge is given as a wrong answer.
Because it is a wrong answer. If it's wrong, then it is wrong, I guess. Okay, let's test it. If BD is forward edge.
At least when I did the DFS with the pre and
What did
post
you do?
numbering, yeah.
You don't need pre and post. Okay, you were trying to go by the actual definition. Formal. Okay, let's do it that way. You started with A, then
Yeah, A is 0, then it goes to B with 1. Then it goes to D.
okay.
So even if you stop here, BD is a forward edge, right?
BD is already in the tree. It can never be
BD,
a
it's
forward
a
edge.
tree edge, no? Your forward edge, back edge, and cross edge. All of these are non-tree edges.
Should not be
Yeah.
a non-tree edge. Okay, thank you. I understood. Understood.
Okay.
Thank you.
Anything else? As we can wrap up the session.
This question, I want to take the screenshot just once. Okay, thank you, ma'am.
Okay, so if there's nothing else, we'll end the session here.
Thank you.
Okay, thank you.
Wait a minute, I have a doubt. Let me check what question it was.
Okay.
One minute, ma'am. Yeah, ma'am. Question number 3, practice assignment. Question.
Yeah, which question? The third?
Question number 3, third.
Okay.
The directed option type graph. Directed and directed
And
cyclic.
practice as you're talking about practice assignment, third question, right?
Yeah, ma'am.
Okay, just 1 second.
It is a sub question of some other part.
Yeah. Okay, I'll do that too. Just 1 second. This is the sub question, and I'll just paste the question too. Just 1 second. And this is the question. Yeah, so what's your doubt?
मैम आई हैव अ डाउट मैम मतलब ये क्वेश्चन में करे कैसे इसको हाउ टू टैकल दिस क्वेश्चन हाउ टू स्टार्ट दिस आई डोंट अंडरस्टैंड
Okay,
करना
the
कैसे
third one actually has, if you're talking about the third one particularly, this has nothing to do. You've been given 3 vertices, this K, S, and N1. So this one, these three, K, S, and N. So if you'll only include this part, and it also says that you have to take E intersection. So E means the collection of edges, right? This is the collection of edges intersecting with V1 cross V1. V1 cross V1 means you have to take KS as one edge, then SK is also one edge in V1 cross V1, and then SN is an edge, NS is an edge, and then KN and NK, right?
yeah
And then you take intersection with the set of edges. So in the original graph, KS is an edge, so you keep this. NS is also an edge, so you keep this. And that's it, right? You only have 2 edges here. So these are not in the intersection because they're not in E, right? These are not there. That means in this set, you only have KS and NS. So in simple words, I've done it this way, but in simple words, you can just directly take it from here. It's this graph, right? And now the question says,
वो डायरेक्टेड एंड डायरेक्टेड बताना है फिर
yeah, so you have to tell if it's a directed graph. It's clearly directed because you have directions here. So this is true, right? And it's a graph because it has edges and it has vertices, and even if it doesn't have edges, that's fine. It's a graph. So this is incorrect. Then this is not cyclic. Obviously, there are no cycles here. There are only 2 edges. 2 edges anyway can't form cycles. So this is also incorrect, and then undirected is incorrect. Is that okay?
yes ma'am one more question and question number 4 the same question number 4 I got the
1 second.
is 7 and the okay
Fourth.
Ma'am,
yeah
in
ma'am
this question, what is E actually?
1 second.
that is E1 E1 is a subset of a edge of a G
E is when you write capital E, it's the collection of all the edges in the graph. So if this is your graph, then it's the
Okay.
collection of all the edges here. And this one asks about If Joe is hosting the party, then at most how many members can join the party? So Joe is here.
Everyone, ma'am, here everyone can join. Only these two, Shiva and Christy, will not be able to join because there is no way go back.
Right.
Yeah.
The rest
So
8 can join. Yeah.
these two can't join. Everyone else can join this
The
party
rest is only 7,
at
right?
Joe's
The
place.
question is slightly twisted.
1, 2,
Joe should
3,
not be
4,
included in the
5.
answer, no?
Yes, ma'am.
No, I
But the
mean it's
answer,
what does the question say?
the correct,
That
no,
yeah,
please.
it should have 7.
But the answer
The
given is
answer is
8,
8.
actually.
But Joe technically Joe can attend the party too, so that makes sense.
I mean, it's a
It's
question of
8.
interpreting whether Joe should be included or not in the count.
I understand, but
Ma'am,
it's
if this type of questions
we're
came,
including Joe. What?
if this type of questions came in exam, so should we choose option 7 or 8?
If you're given questions like that, you'll be given marks for that. You'll be given marks for both. Won't be given ambiguous questions like that.
Ma'am, the
Okay.
last part, can you explain like how it is 8 like from the beginning?
Okay. The question asks how many people can join Joe's party. So if you include Joe in it, it will be 8 people. If you don't, then it will be 7 people. And how do you get 7 and 8? It's you can just check directly which are the vertices from where you can reach Joe's place. From here you can reach this. Here also you can reach this. From this point also you can reach Joe. Here, from here. Here you don't have a direct edge, but you can reach from here. Here and then here. So from here you can reach there. From here also you can reach there. So only these two cannot reach there because you don't have an edge here. That's why these two people can't reach this place. In fact, they can't reach anywhere. These two can't reach anywhere.
Even ma'am, Nia cannot join Joe.
Nia can, right? This is
Ma'am,
the
it's
path.
the ma'am, the arrow is from Vishit. Okay, okay, it's both the arrows. Okay.
It's both ways. Okay, anything else?
Counting the number of
Ma'am,
arrows, it would be 8, ma'am, in a way, you are saying.
No, it's
The
other
vertex.
than the
Okay, okay.
total 10 number of vertices, and if you
Okay.
subtract these two,
Yeah,
you'll
ma'am.
get 8.
Okay, okay.
But if you exclude this person too, it will be 7.
Can you please explain tree edge once? I'm confused on that part.
Okay, tree edges are basically the ones that are present in trees. So when you make a BFS tree or a DFS tree, that's when you talk about tree edges and non-tree edges, right? So BFS, you have BFS, DFS trees. I hope you know how to you're clear with BFS, DFS trees. That part you're clear with, right?
Yes.
Okay. Then the ones that you see in the BFS or DFS tree, those are tree edges. And in BFS one, we actually don't talk about the tree edges and non-tree edges, right? We only talk about that in DFS one. So in DFS one, the ones that you see in the tree, DFS tree, those are tree edges, and the ones that are not there, that means they're in the graph. So if you have this graph, A, B, C, and these are the edges, and then your tree would be like this, right? Your DFS tree would be this. It would actually be a straight line. That works too. A, B, and C. This will be it, right? This is your tree. This was the original graph. A non-tree edge, because you have A, B, and C, that means your AC is a non-tree edge, right? So the non-tree edges that are not here. And then in that case too, you have 3 types of non-tree edges. So one is forward edge, then there's back edge, and then there's cross edge. So forward edges are the ones that are pointed in that. In simple words, if you don't want to go by the definition of post and pre numbers, you can simply take, if this is a cycle, and if you do this thing, so if you take C to A, then that's a back edge because it closes a cycle, right? It is helping in forming a cycle. That's why this is a back edge. And if you take A to C, That's a forward edge because it's opposing the cycle. But when you deal with bigger cycles, this is a three cycle only, so it's easier here. When you deal with more numbers here, like this one, and in fact, if you deal with 5, that will be even more difficult. So it's big. If you have this thing, then you can clearly see that this arrow is opposing the formation of cycle. So you can tell that this is a non-tree edge, then it will be a forward edge, right? But otherwise it becomes difficult. So how do you check for bigger cycles? You simply have the definition of back edge and forward edge. So if you have AC, the forward edge says that if it should be pointed towards the downward thing. So you should have what's the just 1 second. So in a forward edge, it's a forward edge. If AC is given there, then you take pre number of C and post number of C, and then check if it's contained in pre post number of. So if that means the C thing should be contained in this. So if AC is given to be an edge, if AC is the given edge, then you check the pre post number of this, the interval that's formed by using the pre post number. That should be contained in this interval. What does it mean is that this thing came later. That means this came first and this came later, right? That forms a forward edge. If you have here you have 1, 2, and here you have 0, 3. That means this thing came later, C1, and the A1 came before this. Right? That's why you started with A first, then you started with C, you got done with C, and at last you got done with A. So this is called the parent or the ancestor. So if you have the parent here, the parent or ancestor here in the first position, then that's a forward edge. But if it goes other way, then that's a back edge. Back edge is the opposite of this forward edge. Is that okay?
From a
If
numbering
we
point of
create an
view,
edge,
sorry, from a numbering point of view, how do you determine backward? It was not clear. Forward understood because 0, 3 and 1, 2 are within 0, 3. Can you give an
So
example,
let's
please?
say you have, let's say these edges, this is pointed both in both ways.
Bidirectional.
So you have this, and this number is 0, 3. So this is post number, pre number, post number for A, and this
Correct.
is pre number, post number for C. Then if you take AC, that's a forward edge. And if you take CA, that's a back edge.
No, I'm just trying to understand from pre-post numbering and what is the formula or guidance for suppose AC is not there, let's say, but CA is there, but it is a non-tree edge.
This, if you have this thing, and pre-C, post-C should be contained in pre-A, post-A. That means this one, the one that you've written later, pre-post number of that should be contained in the one that's written first. That's for forward edge. And in the back edge, it goes the other way. That means this thing should be contained in this thing.
Oh, reverse of this.
Yeah.
Can you just make a diagram of both of them?
Both of what?
The pre-C, post-C contained in pre-A, post-A. That you said it's a backward edge in a way. Yeah. Can
I
you make?
just did it here. Do you want me to like take a proper tree and then do it?
No. Just normal. This is the both, na?
should there be an arrow for defining it, back edge and forward edge, right?
Just
In
yeah,
directed
ma'am.
graph,
Just
you always have
just the
arrows.
arrow thing, if you can make it, because A and C, yeah, for both these two.
In a directed graph, you have arrows, and when you don't have arrows, Let's say you're taking an undirected graph, you're taking it this way. Then that, okay, let's say you have this thing. Now, if you'll make a tree, you'll have A, B, and C. Obviously, you'll have to take some arrows here. So you'll be taking, either you'll be taking both ways, then it won't make sense here, right? Now, if you'll take AC, this thing, because typically one arrow means when you take undirected graph, it means it's both ways. In an undirected graph, a single arrow means it is usually considered in both directions. That means you can't actually discuss these things, back edge and all, when you don't have directions. So only with directions you can do these things. And when you have directions, it's clear with what we do with directions, right? If you have these directions, then you have A, B, and C in this order. And then if you're taking CA, then this is, if you number these things, you got started at 0, then 1, then 2, then you got done with C, 3, 4, and 5. And now you're 0, 5, to check for 0, 5, and 2, 3. So 2, 3 is contained in 0, 5, right? So if you're checking for CA, and the pre-post number for C is contained in pre-post number of A. It's like this one. It's a back edge. Is that okay?
Ma'am, what should we look for when we are trying to determine whether it is a back edge, forward edge? What are the criterias, rules?
Rule is first it
Right,
should be a non-tree edge, so it shouldn't be present in the tree.
Okay.
First rule. And then second rule is you just check these intervals. Just mark them with the post numbers and just check these things. That's all. That's it.
Ma'am, your
If
voice
it's
is not
CA,
clear. We can't hear properly.
is it clear now?
Yeah.
Okay. The first rule is it should be a non-tree edge, and then second one is this is the definition for it. So if you have AC, then for forward edge you should be taking, I'm not sure what you're asking because I've already written the definition. What exactly is your question?
It's okay, ma'am. Yeah, fine.
There is one doubt, ma'am. Here you said that in this diagram that you made, you said that it's a back edge. If you just go a little up here, you said it's a back edge, that is CA. That's why you wrote 2, 3 is contained in 0, 5. Yeah, ma'am.
Yeah.
Suppose if it is a forward edge, then we would have written like 0, 5 contained in 2, 3. Na? The order should be changed. That's all.
But 0, 5 is not contained in 2, 3. That's why it's not a forward edge.
What, ma'am? Suppose if it's a forward edge, then what is the structure to write?
Then it goes other way.
Yeah.
It goes other way, but that's not true in this case. That's why it's a back edge.
Yeah, ma'am. If it was, if it would be a forward edge, then it should
Then
be
it would be reversed. Right.
Yeah, that's.
With help of adjacent list, can you help me out to find the edges and degrees?
Okay. What?
The adjacent list, if they give an adjacent list,
Okay.
can you find that number of edges and degrees if they given?
Yeah, you can find with the help of adjacent lists, you can actually construct the whole graph. And from there, you can find everything. If it's given to you,
If
let's
they
say
given
A,
adjacent list, we have to draw a graph and then only we can able to find.
yeah,
Is
if
there
you
any
don't
easy
want
way
to
to
relate,
identify that with that
if you
list?
don't want,
We can easily. Yeah, go ahead.
yeah, we can do that. If you don't want to get into the graph and all, you can directly use this thing. But sometimes it's just easier to draw the graph and then see things from there. So if you have this thing, let's say this is given to you and you want to find the degrees of this if this is directed, let's just take this to be a directed graph. And you need to find the in degree of, let's say, A. And this is because it's directed from A to C, right? So the in degree of A is 1. So you can just check where A is present. So you don't have to like get into the graph then. You can just check where in which list is A present, right?
Okay.
That will give you the in degree. So here it's only present in this one, C, so the in degree should be 1. And for the out degree, you can check here. So for out degree of A, you can just directly see this. Out degree of A will be 2. Is that okay?
I'm sorry, I'm not getting. Can you write it in the numbers with this A and B? I cannot.
Okay. Let's do this thing. If you have V1,
Yeah, yes.
taking this to be undirected, otherwise I'll have to adjust things. So let's take this. So if I try to find the in degree of V1, in degree means the number of edges coming towards V1, right? Pointed towards V1, this
Yes,
thing.
yes. Yes.
So that means, and this is going from this to this. So you just check where V1 is present. So V1 is present in 2 lists, right? Here and here. So it
Yes,
should be
correct.
2.
Okay.
And then if you try to find the out degree of V1,
Okay.
you can just directly see it from here. So there are only 2, so you can write 2 here. 2 from here. Now it's 3. Is that okay?
No, only 2 only, ma'am. How it is coming? 3?
It's V4. I've added V4 in this list. V4, V2, V3.
Okay, okay.
Okay.
Sorry, one more doubt on that. This one, forward and backward. In that example ABC that you gave, if you scroll up please on the right side. If
Yeah.
AC is in the ABC example, where was it? If AC is bidirectional, then it is both forward and backward edge, right?
No, it's not both backward.
No, if for some reason if the graph is
If
given in
it's
such a
both
way,
directional, you can't have it in such a way, right? If you have this thing, if you have A and AC is in both ways, so you start with A, then you go to B, C, and then you end at C, right? It ends at the DFS tree is not going to change, and the numbering is also not going to change. If this is the tree given to you,
correct. If AC is
and
bidirectional,
one more tree is possible here, which is this. Now, if you make it like this, one more tree possible is AC, and then you go back to A and then to B. Now it will be 0, 1, 2, 3, not 3 here,
it will be 5 only there. Yeah.
3 here, 4 here, and 5. If this happens, then things change. So the DFS tree will be given to you. And if it's
So here,
not given to you, then you have to consider both of these.
Okay.
Every possible DFS tree.
Ma'am, the BFS tree that you made ABC, you said that CA is a backward edge. That's why you said 2, 3 is contained in 0, 5. Yes, ma'am?
And in this one.
Yeah, ma'am. Can you just give an example of a forward edge to just write it in a way, the structure of that? Just.
Okay, for forward edge, you need this thing. A, B. This works here. So you will have A, B, C, 0, 1, 2, 3, 4, 5. If you will do this thing now. Now your edge is CA, right? And 2, 3 is, by the definition, let's see the definition of forward edge. It says that the pre-post number of the one that's written later. The pre-post number of A is 0, 5. The one that's written later is A, right? C, A, right? Wait, the one that closes your cycle is a back edge, and the one that okay, so you should be taking it in this way. This will be a forward edge. The one that closes your cycle is a back edge, and the one that opposes the cycle is a forward edge. So this will be a forward edge, and you should be taking AC here. So if you take AC, as per the definition of your forward edge, the one that you write later in this edge. So C is written later. So you should be writing the pre-post number of C first. The pre-post number of this should be contained in pre-post number of A, right? So pre-post number of C is 2, 3, and it's contained in the pre-post number of 0, 5. So in this case, your AC is a forward edge. Is that okay?
Yes, ma'am. So
Ma'am,
in a
BC
way,
will be
we
the forward edge too.
BC is already part of the tree.
In this particular tree, BC is a part of the tree. But if you start from here, A, then you go C, then you go B here. So it becomes like this: 0, 1, 2, then 3, 4, and then 5. Now, if you take BC, it's a cross edge, right? Because 1, 2, and 3, 4 do not have any intersection. It's empty. So now this thing, which is a non-tree edge, let me just draw it a dotted line. This is a non-tree edge, and this is a cross edge. Is that okay?
in the example, when you wrote the forward edge AC 2, 3 contained in 0, 5, we can say that A is the father of C in a way. Like A is like C is the son of A in a way.
Yeah, you can say that. Okay, anything else?
No, ma'am.
Can we end the session here then?
Sure.
Thank you.
Okay. Thank you. Bye.
Thank you, ma'am.
Thank you, ma'am.